there, so never like. I decided I.
Good afternoon, everyone. Welcome. I hope everyone had a restful reading week, or at least didn't have to take classes. So today's speaker is Sihan, who received his bachelor's degree from Lanzhou University in China, received his master's of engineering science from Tongji University in Shanghai in China, one of the best universities in China. And then he came here for his PhD, and he graduated in 2015, supervised by Dr. Han Ting-hong, who recently graduated, or sorry, recently retired, not graduated. And thankfully, he's been able to come back and give us a presentation on what he's been working with these days at RWDI on wind engineering. So with that said, thank you for coming back. Thank you for making time. The floor is yours. Okay.
Well, thanks for Dr. Bingley's introduction. As we just mentioned, I am also a graduate from Western University, and about 10 last years ago, I sit in the States as you guys, get inspired from other people's talk, and I'm so pleasant to get this opportunity coming back to share some of the research findings and work experience that I've accumulated after I graduated from here. Today, what I want to share with you is related to some of the hot topics these days related to climate change. So my topic is about achieving climate change adaptation and resilience by updating building design code. I have a couple of relevant experience currently being the chair of the Committee on Adaptation to a Changing Climate under ASCE, and co-chair of ASC 728 Future Conditions Subcommittee Wind Task Group, and also being very lucky to be part of the lead for the National Building Code update under the Climate Resilience Initiatives. So I would like to introduce or share some of the experience we have been through in the past couple of years through 4 pillars. The first one is the role of the building code in climate resilient society and its importance of the climate modeling, and why we need to adapt to a forward-looking design philosophy. And lastly, just to go beyond the minimum requirement of the code towards a forward-looking performance-based design. Let's go back to the first point. What is the role of the building code in a climate resilient society? As civil engineers, after you graduate, get your professional engineer license, etc., you have to always comply with the code requirements for any of your practices, construction, design, maintenance, etc. And there's a reason why code is so important for practical experience practices. And there's just a couple of documents, reports have been recently published and identified the importance of that. And one of that is interesting, you can see, is the World Bank Group published a report on building regulation for resilience. It points out the building code implementation has a critical role to play in disaster risk reduction, one that until recently has not received adequate attention. And there's a couple of reports in recent days. One is from the States, the National Institute of Building Science published a report on the multi-hazard mitigation council report. It concluded adopting modern codes save $11 per $1 spent. And similarly, in Canada, our own Western Institute, I think it is the Institute of Contractual Laws, Research Institute published a similar report saying the total benefit cost ratio is 12 versus 1. Basically, you receive $12 benefits by spending $1 to do the mitigation and adaptation. And also the Canadian Climate Institute recently concluded similarly that $1 spent today for mitigation measurement, we will receive $13 to $15% in return in a year's coming. And now here's a couple of active initiatives. Some of them have been finished and some of them are still ongoing. The one that Canada is so proud to be the leader in this field, led by National Research Council and funded by Infrastructure Canada. In the past around 5 years, there is a climate resilient built environment initiative This initiative has about 150 partners, not people, it's partners. The people behind of those initiatives are even more. Produced many stands, codes, practices, guidance, tools, data to support Canada in the positions to be resilient in the future. And these are just some of the examples I have listed here. So including the resilient climate resilient buildings and code, public infrastructure guidelines on durability of building, like the CSA group climate change adaptation for wastewater treatment plants, etc. Similarly, in the US, recently, between the American Society of Civil Engineers and NOAA, which is the Climate Sciences Community Institute, has written a memorandum in terms of building up the initiative to do a climate resilience engineering practices. And the ASC 7 building code, which is widely used in the US and referenced worldwide, has established a future conditions subcommittee in charge of developing a particular chapter to prepare the community for designing for climate change and other future conditions. So that being said, many of activities are put a lot of efforts. People are on board to prepare for the future conditions in terms caused by the climate change. And it goes back to the second pillar is the importance of the climate modeling. Before I go to a little bit in depth, so just to give you a little bit of background in terms of why Canada would can lead the forerunners now in terms of this field. Partly because the Canada's building code infrastructure are actually designed based on the code which developed purely based on historical data. There's no account for the impacts of climate change. Canada's climate impact is actually is warming on average about double the magnitude of global warming. Now, one of the plots I have put it here to give you some visual evidence. On the left, what you can see is the average global warming. And on the right side, the panel is indicating the average temperature anomaly that what we see or what we're going to expect in Canada. And you can see we're faster and we're more intense in terms of the increase of the temperature. And that only gives part of the reasons why we have to be the forerunner to prepare this community and this nation for the climate change. But also, future climate created non-stationality or terminology many people may not be familiar with, and I will get into that point, but that is one of the primary reasons why we cannot continuously using the historical data anymore, because things is changing than what we expected based on past experience. Here we give another some, let's see if I can have that, probably not, okay, never mind. Here are some other plots showing the temperature change globally. And also, oh, that works. Oh, yes, I have video. That's great. So what you can see here is prepared by NASA's Scientific Visualization Studio. Now, when you can see the temperature change, the distribution of the temperature change is not only a shift, but the entire shape is actually changing over the time. Here is some more evidence on this panel. This is basically the latest observation based on ERA 5 produced by European meteorology community that is indicating our entire atmosphere temperature is rising faster, or at least expected it as RCP 8.5. which what I'm gonna give you a little bit background just in a minute. So here are some key points that you can take away in terms of why climate modeling is important in the contents of preparing the community for a resilient community, the future. When we're using the climate modeling, the level of confidence given to the projections of the change or direction, pattern, and overall magnitude of change based on supporting evidence and precise understanding. So you cannot just grab the data and use it as you thought that is fully reliable. You have to have a better understanding about what you're using, what is assumptions, what is limitation to kind of fact. And assessments can be done at different spatial scales, from the local scale, regional scale in terms of city, province, and national scale, which is probably one of the largest scales you would like to use the data. And also the suitable application of this data will be strongly depending on the level of confidence in terms of scientific confidence you have to the projection, to the scales you use the model to be used in your engineering practices. And there's two uncertainties oftentimes engineers are not very familiar with dealing with. One is epistemic uncertainty, another one is aleatoric uncertainty. And those two uncertainties oftentimes are not fully understood or communicated. But when you're doing or using the climate models, and those two uncertainties have to be well understood and understand which one might be governing when you do the application. And another important thing to think about it is when the warming going to occur to the level that expect. So time becomes important. Come back to the time becomes important topic, and here's our two things you can get a good sense why timing for warming can become an important parameters. As I just mentioned, the left panel is the ERA 5 recent observations in terms of global warming. Now this year is 2024, so this data only showing by 2023. But what you can see is the past winter, what we see, the average temperature anomaly has been exceeding 2 degrees Celsius, which is actually not good news. But what interesting things you can see is on the right side is cluster average predictions by using different climate modelings across the entire world, which is available. And interesting things for that is if you see the relative period, which is around centered about 2000. So this average temperature change is relevant to 2000. And what we can see here is by 2000, if you see what our observation tells, we are average about 0.5 to about 0.75 degree increase compared to the pre-industry, where we think the human activities caused by the greenhouse emissions hasn't been injected to the atmosphere in long enough to get the reactions. So now put that 0.5 in your mind, because what we're going to do is we're going to put this 0.5 on top of that. So which basically means all these predictions going to give you a timeline to see how it do its work, tracking or predict how the global warming going to be. So if we put on top of that, so we're expecting 1 degree to 1.5 degree. Now RCP 8.5 saying by 2023, you're going to see the average temperature anomaly going to be roughly reached by 2023. RCP 4.5, 2022, RCP 6 by 2025, and RCP 8.5 by 2020. So 2020 is 4 years past. So if you're looking at the observation curve, which is just below the 2023, what you can see is somewhere here. So that is just about a 1 to 1.25. So by so far, the RCP 8.5 is still tracking the global warming temperature, which somehow is not a very good news, because it's saying we need to do a lot of things to do the mitigation, really drop down the temperature increase. But on the other hand, from adaptation point of view, using RCP 8.5, at least up to now, it seems to still a reasonable choice. Now, all this has established a baseline to tell you it is important for us to using climate modeling to consider the climate change. So coming back to see what is that matters for engineers, oftentimes we're actually don't dealing with this climate outputs at all. Or if we're using historical data, oftentimes those data are collected by meteorologists or others which are not engineers. Now let's review the engineering practices, how we use the historical data, how we get all those design variables in a conventional practice. So these plots give a general idea how we use those data and how we think we can project our load, which is the natural forces, and impose to all the structures we want to design and build. Now the conventional practices we would collect all those data, which is just in this right square box. We think that is good enough, and we consider that stationary. So what we call is stationary is something we think the characteristics of this data does not change with time. Whatever you quantify in terms of mean standard deviation, or you call it 50-year return period or 100-year storm, will not be changing with time if you do the projections in the future. And this is exactly validate when you have stationary data. So in that case, we only need to consider historical data. We can derive the return period or any exceedance probability design values in the historical data. And the annual exceedance probability can be easily transferred or transmitted from the annual exceedance probability to a total probability, because annual exceedance probability are constant in a stationary class. And when you're dealing with reliability, you're often dealing with annual probability of failure, and then you can easily derive that to a total probability of failure. Because again, it is a stationary climate, it doesn't change with time. Now, having a non-stationary climate caused by climate change gives you a lot of change and challenge that you cannot using the conventional methodology anymore, because the climate becomes a time-dependent variable or temperature-dependent variable, which also can be interchangeably connected to each other. Now, because of that, you cannot reliably using historical data to do the projection anymore. You have to now employ climate projection. Now, the future service life become a problem because you have to know when that target warming or target time going to occur. You need to prepare your structure for it. And now you cannot using an annual exceedance probability anymore because that changed at the time, all the time. So you probably have to using either what is a maximum annual exceedance probability or what is maximum lifetime exceedance probability to prepare your infrastructures. Now, similarly, you cannot using annual probability of failure anymore because that becomes a changing variable. You probably have to be using maximum annual probability of failure, or maximum total probability of failure throughout the entire service life of this system. Now, before we get into the non-stationality, there's one thing we have been working on and proposed an update for the National Building Code of Canada. Is a transition from what we call a uniform hazard approach to a uniform risk approach. And this approach actually has been used by many other codes like the ASCE building codes, Australian, New Zealand building code. So what you do is when you don't have that uniform risk approach implemented, you would always have a so-called load factor. I don't know how many of you are familiar with code. If you do all of your design based on the code approach, if you do wind design, or you consider flat design, or you consider seismic, you will always have a load factor. Engineers like using factor to quantify the uncertainties, to envelope the uncertainties that are out of our control. You have a lot of uncertainties throughout your design, your construction, and maintenance, etc. You're using a factor trying to envelope those uncertainties that's are not exactly controllable by engineers. But what we found in a past research, I collaborated with my former supervisor, Dr. Hanbing Hong, and also a following study that he did with his research group, is basically have the same conclusions. That using a single load factors across the entire Canada with a large variability of the climate actually give you a very large range of reliability index. A reliability index that has been used many years in the engineering community to communicate the structure safety. Oftentimes we're using 3.0 as a target. But as you can see from these plots, Now, considering the variability of the Canada across entire Canada, now that has a very large variability of your reliability index. It's really depending on where you're going to build your structure. You might hit it, you might underestimate it, or you might overshoot it. Now, however, if we actually reduce that load factor to E1, but coming out a different return period or any exceedance probability, basically scaling it up a little bit higher. Currently, we're using a 50-year return period. Now, if we go up to 500-year for wind or 1,000-year for snow, what you can see is that the uncertainty becomes very, very small. Now, it's only about 0.1 or 0.2 go up and down around the target. Now, if you convert that back to the probability of failure, it becomes even smaller. It's probably very well within engineering accuracy that we can control. So that's one thing that has been proposed, is just moving from uniform hazard to uniform risk. Now let's coming back to the climate again. The one thing I have mentioned, we cannot continuously using the historical data anymore. And now the immediate question is, can we using historical data to detect any trend that has been caused by climate change? And using that as a guidance to project that trend in the future. Now, this is one of the efforts we have been made by taking about 20 cities across Canada, collecting all those wind speed data, and of course, doing the quality control, standardization of the wind speed, and then doing some trend detection analysis to understand whether in the past 50 years, whether the climate change has affected the real observation significantly enough so we can use using that trend as a guidance. Now you can see the linear fade is basically indicating some trends, but that doesn't mean whenever you see it's not a straight line, it's not a horizontal flat line, it has a trend affected by climate change. It only showing you might have a linear trend, and you still have to do some statistical significance test. And that's going back to the two uncertainties I just mentioned. One is epistemic uncertainty, the other one is aleatorial uncertainty. So one is talking about whether you have enough sample to tell this is a statistical significance observation. Another one, it only tells whether you have enough knowledge to understand what you have observed is true. Now, anything, if it cannot pass the statistical test, is basically saying it's less likely caused by climate change. It might be caused by something else. The data measurement, the anemometer change, the terrain surrounding change, and something else. And also, we have also doing something to see whether the change has seasonal variabilities and whether that change with different directions. And what we can tell is there are some change that you can tell from historical records. But what we found is even challenging is it's hard to say or conclude confidently those changes are caused by climate change because there are so many other factors affected into it. And it's very hard to entirely filter out those causes. Now, because of that, now we have to employ the climate modeling outputs, and this is one of the climate modeling outputs that we got from Environment and Climate Change Canada during that large national research initiative. And this one, I gave several examples on the right, and those are the true simulations. You can see from top to down. They can see there are locations that you just don't have climate change impact at all. And the bottom one is one of the obvious trend that you can see the impact of climate change is significant, and you would have to consider the non-stationary climate. And all those color plots, the top panels, I think it's the trend detected for extreme wind speed. On the left is the mean detecting the trends, and on the right is the standard deviation of that detected trends. The bottom plots are the trend detected for ground snow. Again, the right plot indicating the standard deviation. So you can see again, even if we get the climate change, climate models, we still have a large uncertainty in the model. And you can see the standard deviation for some locations are quite large, which basically means not just have got one climate simulation and use that for your practice, because climate model itself generating a lot of uncertainty. It's coming back to see what are the key parameters when you do a forward-looking design philosophy. The first one, of course, is you have to using climate projections, but you would still have to using the historical observations as your baseline. Now, two periods becomes important. In the past, we actually don't really care too much about the future date, although there's always an implicit assumptions about how long our structures would serve. Oftentimes, building assume about 50 years of service life, range 75, 100 year service lives. But actually, other than that, it's not very sensitive in terms of how you quantify your design loads. Now, when you're dealing with a future climate, especially non-stationary climate, now baseline and target period becomes important. Now, here's a reason why it becomes important. The top plots, what you can see is a stationary climate. You can see the determined design value can be a constant throughout the entire service life. You really don't care whenever your capacity of your structures are not going to be deteriorated throughout the design life due to some environmental and other loads. If you're assuming your capacity is the same, your design loads won't need to change at all. Now, if you have a non-stationary climate, which is the second case at the bottom, now that becomes tricky now. Now, if you quantify anything based on historical period, what you're going to get is the lowest design values. And you can see it's very easy to be exceeded in reality, even during the design, assumed design life. Now, depending on which time and what methodology you picked, now you can have 1, 2, 3, 4 or more design values to be used. Now, if you do not define a clearly future condition, either depending on warming or depending when you want your structure to stand there or how long, then that becomes your engineering and design challenge. Again, from a purely reliability analysis point of view, it becomes challenging. Well, now these plots representing or calculation of the total probability of failure, which is on the left panel, and also any probability of failure on the left panel. And you can see the horizontal line representing the significance of non-stationality. And I have plotted two curves here. The bottom one representing 10 years starting from the start of your service life. The upper one is the 50 years from the start of your service life. And you can see there's a significant shift of your probability of failure. The bottom plots probably give you a better leader indication. The solid black line, we're trying to maintain our safety or reliability of our structure. And all those dashed lines indicating if you do not prepare your structure for a future climate, and this is a probability of failure you're going to expect in the future throughout this design life. And you can see the magnitude of increase or decrease of the safety is significant. But coming back to see, now we know we have a challenge in engineering practices and what are we going to do with it? There's a couple of methodology has been proposed in the literature. And overall, they're basically just two groups because many of them are calling different names, but they're actually quite comparable. Ended up with very similar results. And one example is here, we pulled them together and we calculated based on different non-stationality. We found most of them are same, except that there are two methodologies have a little bit different design philosophies. One we call is min-max design life value. Another one is design life value, which is DLL. Here's a graphic indication of how you do your design based on these two different methodologies. Now this curve representing the probability distribution. Now, because it is now becoming a changing climate, so your probability distribution change with time as well. Now, what you do using this minimax approach, what you have to consider is you have to define the service life or end of your service life. And then within that period, now you have a different probability. And you have to select your design value to ensure the maximum exceedance of that probability maintained to your target level. And this is what we call the minimax. So it's not necessarily happened by the last year of your design life because it's totally random precise. And in some cases, you might actually get an increase of loads and then decrease of the loads. Now, the DLL approach is a little bit more complex, but somewhat more flexible. It gives you the selection of your window. It's not calculating the annual exceedance probability or any in that window. Is actually calculating the accumulated probability exceedance or the accumulated total probability failure within that window. That basically means this window can goes along with your true life, actual life of your structure. And getting close to the original design life, you can adjust that window to see how many years of remaining service life you still want for that service life. But again, it's because it's more complicated. In some circumstances, it might not be fully practically applicable because there's so many things you need to consider. Based on all this approach, one can develop the climate change factors to scaling up your design values. Based on different exceedance probability and assumed service life. And similarly, you can do wind, snow, and other things. So here is basically extension from Canada to entire United States. And one thing interesting to see here is on the left is the target year is 2075, and on the right is the climate change impact by the end of the century. You can see some of the areas are actually not changing too much, but there are some areas like British Columbia, California, Florida. You can see if you change your target year, the climate change would have more impact when you're getting close to the end of the century. And this is another example is for snow. Majority of locations across Canada, we expect snow loads in a warming climate, but that doesn't mean we can reduce the design snow loads because at the beginning of your infrastructure design, you still have the maximum loads. So the factor would have to be limited to 1 if you have warming climate, but you still have to use in the present design value. But if you have impacted climate, and that's what goes up the snow loads, you would have to increase the snow loads for that during your service life. Here's just another examples when we combine two things together. One is the hazard, the probability. Another part is the capacity probability distribution. Now, rather than just having one part exceedance probability, now you're actually having a two-joint probability to deal with. And this is just for dead load and, for example, dead load snow load, dead load wind load. If you have live load, it is not going to be a two curve interacting together anymore. It becomes a surface, is a volume if you have more and more parameters getting involved. But generally, it's have the similar idea, whether you have to select or service life to quantify or target any probability of exceedance or probability of failure. How you move your window to understand what is a total failure within that targeted period. And here's just two examples to see if we design the structure to consider the forward-looking design values incorporating the climate change, how your probability of failure going to look like. The top part is the annual exceedance probability. Again, the solid horizontal line is our target. As you can see, by the end of the service life of 50 years, you're roughly still around the target. You might get a slightly exceedance, but you are still very close. Consider the variability that I just showed across the country. And that generally is acceptable engineering accuracy. And similarly for the DLL, and you can see it's also doing the same things, but a little bit different things here is the DLL gives you a little bit more safe that you can use if you want to extend that service life in the future. Those examples are when you consider not only wind load, tide load, but you only want to consider light load. So you have 3 or 4 loads to consider to design your structures and how your climate change impact would be affected, affecting the your reliability, and when you're incorporating the future, the forward-looking design values, how that's going to go back to its original value. On the left side, what you can see is in the stationary climate, and this is the target probability of failure under different conditions used as a reference. And on the left middle panel and the right panel, all the solid lines are the case that if we do not consider climate change in the design values, and that's your probability of failure going to look like. And if you compare this one, the top dash curve, to the solid right curve there, then you can see that's a significant change. We do not consider the climate change impact. And by the end of your service life, under that climate change impact scenario, you could have a significant impact on the safety of your infrastructure. But if you incorporated climate change into your design, which is going to be go back to this right dash line there, now it's basically getting back to the target value you're preparing for. Giving all this evidence and different methodologies and uncertainties in the climate modeling and suggestions from the climate modeling communities suggesting, now we have recommended regional climate change scaling factors for wind and snow loads for different provinces. And those values, as demonstrated by the previous slides, if incorporating those values into your design values and the future climate impact can be well under control for the structures and achieve that climate resilience. Now, here's just 2 maps showing only for illustration purpose, because there are still something ongoing under development by Environment Canada. But these are the generally indication of the geographic distribution of the design wind pressure and ground snow loads if you incorporate the climate change factor into consideration. Code as a minimum design requirement is oftentimes covered generic design cases, but they're all, as engineers, you're always dealing with very specific design cases that code might not be well prepared for you to design your structures. And one thing we have showed, transform from the uniform hazard to uniform risk approach, you can reduce uncertainty of the reliability index. But even that is still haven't got a truly uniform risk, because your reliability index is still change for the climate. So another thing one can do is, on top of that, to have another factor, climate variability factor, to fully incorporate the variability of the climate and to get the true uniform risk or target reliability-based design. And for this cycle, I think in the National Building of Canada, I don't think this is going to happen. But there's a good examples in the US. The ASC 722 snow loads has used a similar approach using a target reliability-based design value. It's reaching the same reliability across the entire states. So those loads gonna vary location by location, but you're gonna reach the same reliability targets. The second thing is the service life. Now, whether you are assuming that it's 50 years, 75 years, 80 years, or some other years, it is assumption, and it could change with different conditions. Some structures you really want it to stand there for a long time, like residential houses, etc. You probably want it to stand there for 50 years. if it is a commercial building, it's very expensive commercial buildings, in the center, city center like Toronto, you probably don't want to tear it down after 50 years. You probably want to stand there for 80 years or 100 years or even 150 years for some other historical buildings. Now, in that case, you would have to consider your design life becomes an explicit parameters, how you prepare for it. And there's some other methodologies you can do that. And lastly, for wind engineering, there's always an implicit assumptions. I don't know how many you're familiar with that. We always assume a 1 hour duration windstorm. We're prepared for that. We have the peak responses during an hour, but the reality is that a study that I have done with Greg Cobb, from here, what we found is the duration can be longer depending on what return period of wind speed you were talking about. So that hasn't been fully explored in the engineering field, but it can be important parameters, especially if you're doing the performance-based design. You're pushing your design capacity from elasticity to inelasticity, and that parameters can be an important parameter to consider. And lastly, climate change is not only affect structure safety, it is also affect sustainability. And you probably have seen a lot of news talking about renewable resources, when energy is a great tool for mitigation to reduce the greenhouse emission, but it itself also will be affected by climate change itself. So you have to balance the sustainability, adaptation, and resilience, because they're interaffected. Now, the plots I'm showing you here on your left side is the climate change impact, the availability of the wind energy. For different seasons, you can see the impact of climate change has totally different impact. Spring, summer, especially for summer, there's a lot of places you would need a lot of energy for air conditioning, etc. And in that case, you can see a lot of areas you just don't have enough wind energy to do that, or significantly reduce wind energy. So that makes wind energy for those locations becomes less reliable, or we have to use some supplemental renewable energy to supplement that. But in spring and winter, and especially for Canada, it becomes more wind energy for the north part. It becomes more reliable and more accessible. And on the right side panel, it is a reliability index change. Consider the extreme wind speed can affect your wind turbine, such that you have to either shut it down or you have the structure failure. And it's basically indicating anything turns into a little bit blue color, means the future climate would pose more threats or increase the probability of failure for the structure. And you can see there are some locations that it does have the potential to increase the probability of failure for the wind turbine. Here's just a 4 general take-home message. The first one is climate change poses non-seasonality for various design climate variables and require revisiting the conventional design method based on the stationary assumption. Second, future projections becomes important in quantifying forward-looking design values, and the associated uncertainties shall be carefully accounted for and well communicated in engineering design and decision-making. Third, in a non-steady climate, the return period would not return anymore. Given the methodologies like the maximum and exceedance probability and other methods like non-stationary extreme value analysis are needed in evaluating design values and updating code. And the fourth, code is generic and may not fit into all cases, and we need the forward-looking performance-based solutions that require more design parameters to be accounted for, be sustainable, adaptable, and resilient. So here are end of my presentation, and if you have any questions, I'd be happy to answer. If you want to get in touch later to ask more questions, you're more than happy to send me an email or get in touch from other social media. Thank you all.
A tremendous amount of work, all in one slide. Questions from our audience? Yes.
Is there any consideration given in code updates to structures that are already standing? So I know you mentioned like historic structures or maybe critical infrastructure, but so is there any kind of consideration these code changes that are being made to improving those buildings to make sure they're able to withstand future forces?
Yeah, I think that's, so if I understand your question correctly, so for those existing buildings, what we can do?
Yeah.
Prepare them for climate change impact. I think that's a great question. In many cases, existing buildings, people can do retrofitting. If the threats has been assessed such that there's a unsafe of existing structures. In other cases, it really depending on the quality of the construction. And you can see modern codes, if you go back to 30 years or 40 years, it's different than what we have now. And if you even go further, 50, 60, or even 100 years, we don't even have a modern code following. And in many cases, in practices, constructions might build into some conservatism historically. So before we get into assessing the climate change impact to the existing buildings, we have to understand what kind of capacity we have built into that existing structures. So that becomes a critical first step. In many cases, we probably already built extra safety margin there. And we're lucky enough that even if we have impact of climate change, we're just still okay. But in other cases, if we're seeing we're just not enough, and there are retrofitting, either strengthening foundations or shear walls, etc., that can be done. But of course, would have additional cost, and then you would have to consider whether it would be better to retrofitting it and then continue to use it, or maybe just to tear it down to redevelop.
Other questions from the audience? We have time. Yes.
Thank you for this presentation. I have two questions. The first one is actually you as an expert in study climate change modeling. Do you think that it's better to consider countrywide actually studying climate change, for example, for updating the building codes, or we should consider regional actually study? The next question is actually, is it better to consider aging, for example, for buildings, if we should consider the climate change impact on the code or on the building in the future? So should we consider the aging as well?
Great questions. Let me comment on the first one based on my personal view. So whether we use the climate change factors or quantifying climate change impact at larger scale, like province level or national level, or at local level, I guess this really depends. I think based on the consensus we have throughout these practices, depending on what kind of climate variable we're dealing with, if the scientific confidence is enough, like I think the scientific community has a very well understanding about temperature. So that has very high confidence. We know where it's going to go. So in that case, at the local level, is probably very well established and should be considered. Other extreme variables in my less studied, which basically means although we have the variables, but we just don't have very well established either publications or reports or cross references beyond this region. Like, do we really have a high confidence about some, let's say, storm wind, not only within Canada but outside of Canada? Have the scientific engineering community has well understood all these phenomena using climate modeling. If that confidence is high enough, I think at local scale, is reliable. But if that confidence is not there, people can still do that, but there's a potential risk and large uncertainties you would have to take. So the consensus recommendation that we have throughout this cycle for proposing the update to the building code is basically this table here. We're recommending original climate change factors, although those factors has been developed at the local area, and it would need a future more studies to increase the scientific confidence to be able to use that at a more regional level or local level. The second question relating to the aging, I think it's a great question. Because if you do reliability analysis, there are two parts, right? Capacity and demand. Demanding now, it seems we have a well understood, we have climate modeling, we have different methodology, we can quantify how that's going to change. Capacity side is basically material deterioration, aging. I think there are some studies has been done and indicating there could be some impact on that part as well. But again, it's highly location dependent. Like coastal areas, especially very close to the sea or large lake areas, your environmental conditions might accelerating the aging of your foundation, concrete, steel, etc. So those might be something that people would have to consider. What is the impact on the other side of it, and whether that should be considered. But you see, for the design, majority of the cases, engineer only dealing with the loading part, which is the demand part. And material part is addressed by communities like E or something. So they're dealing with the material and investigated the capacity and recommending the capacity or material or safety factors on the other side. So I think that's definitely a good question to consider, and that might, I think there are some ongoing research on the side of the equation to consider what is impact to the capacity side. Yeah.
Thank you so much. I think we won't have time for audience questions, but please feel free to come to the speaker afterwards. I think the room is required for another class. So once again, thank you so much for coming.